In this video, we're going to do another example of testing a hypothesis about a population proportion. And here are basically the steps to hypothesis testing that we introduced in the previous video. So just real quickly, remember we're going to determine the parameter, and I have a little s here because sometimes it'll be multiple parameters of interest. We write down our null and alternative hypothesis. We'll determine the sample statistic, right? So in the case of a proportion, that would be the proportion that comes from the sample. Our p-value, right? And remember, the p-value is, if the null is true, the p-value is how often, the proportion of the time I expect to see samples like mine or ones even more extreme, away from the null value. And then based on that p-value, we compare it to this thing called the level of significance. And so the level of significance can be set at whatever we want to. A very typical value is 0.05. So the idea is I take my p-value, and if it happens to be less than or equal to that level of significance, in this case 5%, then that means that we would reject the null hypothesis. And that's because we don't expect to see samples like ours that often if the null were true. And so since we did see that sample, that means that it's reasonably likely that the null hypothesis was false. If the p-value is greater than your level of significance, that's when you don't reject the null. There's not enough evidence to throw out that hypothesis. And then finally, when we write a conclusion, we want to talk about that alternative hypothesis. So either there is or isn't enough evidence to say that the alternative is true. There is enough evidence whenever you reject the null hypothesis, and there isn't enough evidence whenever you fail to reject the null hypothesis. All right, so in this example, we have a large international company being criticized because only 5 out of 25 people recently hired to management level positions were women. Now, the company states that only about 40% of the applicants for these types of positions were women, and that it is confident the lower percentage of females in the more recent hires weren't due to discrimination or implicit bias, right? So they're just saying, 5 out of 25 might be a little low, but that was just random, right? There's no discrimination, no implicit bias going on. So we want to conduct a hypothesis test to determine if there's enough evidence to suggest that generally the proportion of management level positions awarded to females is less than the proportion of applicants. Okay, now you might look at this 40% number and say, well, it's kind of problematic that you're only getting 40% of your applicants being women, but we're not going to address that question, right? Whether that's too low or not. So we're going to assume, okay, you got 40% of your applicants being women, so we would kind of expect that about 40% of the hires are going to be women. All right, so we'll keep that in mind as we develop this test here in A, B, and C. In A, it just wants us to define our parameter of interest and assign a symbol to it. So in order to do that, we need to think about what type of data we're collecting. So this 5 out of 25 from the sample, what they're doing is they're counting up the number of women in the recent hires. So for each recent hire, you're writing down the gender of the person. So that tells me that it's a categorical variable. We're dealing with categorical data. So therefore, automatically, I know I'm talking about a proportion. So we'll let P be the proportion of management level positions awarded to women. All right, and it's important to understand what we're talking about here. This is just the proportion of management level positions awarded to women generally, right? This is a large international corporation. There's a lot more management level positions than just the 25 we looked at in the sample. So does this provide evidence that generally there's possible discrimination, implicit bias is what we're looking at. So our null hypothesis, remember some of the phrases that kind of go with the null hypothesis are things like the skeptical position, right? No effect, no difference, contains the equal sign. Now, you might not find every one of these phrases helpful in every situation, but usually maybe one or two of them will jump out at you. Certainly containing the equal sign is a helpful reminder. But, you know, if I think of no effect, I think of your gender has no effect on your chances of being hired, right? No difference, right? There's no difference in the proportion of positions that actually where women are hired and the proportion of applicants that are women. So, so both of those kind of fit in their own way. So basically what we're saying is that the null hypothesis is kind of the company's position. And that actually leads to one more phrase that can be helpful, and it has to do with that analogy we gave in the last video about you know, putting someone on trial. Your null hypothesis is that they're innocent. And so we can apply this here. We're kind of saying the international company is innocent of the discrimination, implicit bias. So that's our null hypothesis. So we need strong evidence to move us off of that and take another position. All right, so now that we've kind of established that, I think it's clear what we want to do is we want to make a null hypothesis that says the proportion of management level positions, so just what I wrote up above, management level positions awarded to women is no less than 40%. Right? So 40% applicants are women. We're saying, okay, we don't think that in general they're hiring any less than that proportion. And so in symbols, that would just be 0.4. Now I know no less, you know, might mean 50% or 60%, but the reason we say P equals 0.4 is because it is basically going to be the closest, right? The closest value contained in the null hypothesis to our sample, okay? That's the idea. So kind of make it the, I suppose, the best case scenario, essentially, for the null hypothesis. By the way, this 0.4 that we are that we're talking about here, we refer to this as the null value. So, right, whatever number you're using when you write the null hypothesis out in symbols, that's the null value. All right, so then our alternative hypothesis would just be the contradiction of that, right? So we're saying the proportion of management level positions awarded to women is in fact less than 40%. So in symbols, this would be that P is actually less than 0.4. The true proportion is less than that 0.4. All right, so now it wants us to calculate the sample statistic. So remember, the sample statistic is the same measurement as the parameter, but for the sample. So it's the proportion of positions in the sample awarded to women. So that would be the 5 out of 25 that we're talking about, which is 20%, which is clearly less than the 40% that's our null value. Now in part E it says, how could we simulate the study under the assumption that the null hypothesis is true? So the tricky thing here is in the last video, we talked about flipping a coin. And the reason flipping a coin made sense is because our null value was 0.5, right? So it's a 50-50 chance. Here, that's not the case, right? Our null value is 0.4. So you can probably come up with a number of different ways to do this. You could draw numbers from a hat that has 10 numbers in it, 1 through 10, and if you draw out 1 through 4, that counts as a woman. Draw out 5 through 10, it counts as a man. You could do it that way. Here's another way, and this is the way that the applets that we use are going to do it, is you use a spinner, and the spinner has 40% of its region colored one way and 40% colored another way. So it might, color this in red and color this in green. And so we would say that we want to spin our spinner. So spin, I guess I'll put a little arrow here to indicate my spinner. So spin 25 times to represent the 25 different positions from the sample. Red will equal that the person hired was a woman, and green will equal that the person hired is a man. And then what we'll be interested in is calculating the same calculation as our sample statistic. And so that's going to be me saying that we're going to calculate the number of reds, right, the number of women, over 25. All right, so that is how we can simulate this study. So to actually conduct our simulations, we will go ahead and use the Rossmann chance applet that we used last time. So on our WAMAP page, under Important Class Links and Documents, go down to the Rossmann chance applet collection, and we're going to pick the one proportion inference using simulation. So the previous time we've used this applet in our last example, we left this number here at 0.5, but that was because our null value was 0.5. Now our null hypothesis is that p is equal to 0.4. So because that's my null hypothesis, I want to change this to 0.4. I want my sample size to be 25 so that it matches up with this study. And the other thing I want to do is change the number of successes that I have here to proportion of successes. So this is going to keep track of the proportion of the time we get the spinner on the part that represents a woman being hired. And I'm just switching it to this because you're going to be presented with sampling distributions in both ways. Sometimes there'll be decimals down here, meaning the proportion of successes. And by successes, I just mean the thing we're looking out for, in this case, a woman being hired. And sometimes it'll be number of successes. So just to show both ways. So when I draw a sample, you can see how this works. We spin the spinner, and blue represents a woman being hired, pink represents a man being hired, and 12 out of the 25 were women, and so that gives us a proportion of 0.48, meaning in this simulation, we simulated it, and 48% of the positions went to women. Go ahead and do another one here. So here we go, 9 out of 25. And 9 divided by 25 is 0.36. And so, of course, what we want to do, though, is have a sense of, if we simulated this a lot, how often do we expect results like ours? So let's do this 98 more times and see how that works out. All right, so there's our sampling distribution. Now, before we put this in our notes, there's something I want to note here, is that notice what value is right in the center, right? If this is 0.36 and this is 0.48, then this must be 0.4. So right in the center of this sampling distribution is our null value. And that's what we would expect, right? If we're conducting these simulations with the idea that the true proportion is 40%, then the thing that should happen most often when you simulate the study is to get things around 40%. So that's why we're getting so many right here and fewer out on the edges. All right, so basically, you know, each little jump here is just 0.04. So this is 0.16, 0.20, 0.24, and so on. And to make our chart a little bit more accurate, we'll go ahead and label all of those. So going back to our PowerPoint here. All right, so that's where in part F we want to go ahead and put this. So, and we'll just start way over here at 0. Okay, and I won't label every single one, but maybe 0.2 right there. And I'm doing that one in particular because that is our sample statistic, right? 5 out of 25. So 0.04, 0.08, 0.12, 0.16, 0.2, 24, 28, 32, 36, 0.4, 44, 48, 52, 56, and I got to keep going here, right? And 0.6 right there. .8. And I don't think we had anything much beyond there, but we'll just go ahead and label it anyway. So there's 1. So this is, again, the proportion of successes. And again, successes is just the thing we're interested in. So yes, it's the proportion of successes, but what is it really representing? It's representing the proportion of jobs awarded to women okay, under the assumption the null hypothesis is true. If the true proportion is 0.4. This is telling us how much variation we expect to see if the null hypothesis were in fact true. All right, so let's put some dots on here like we did last time. So just looking back at the applet, and I'm just taking this from the chart we just made, is we've got 1 dot at 0.16. We've got 1 dot at 0.20. We have 3 dots at 0.24. We have 8 dots. There we have 13 dots. Then we have 16 dots. And as I'm making these, just understand this is not something I need you to do every single time. But I'm just trying to make a real clear record of how it is we are getting the results we're getting in these things. I think I made about 19 there. That's how many are supposed to be there. And then another 13. And then 5. And 9. Eight. 2, and 2. So we got a total of 100 dots there. And so remember, each dot represents one simulation. So in part G, when it asks for the p-value, understand it's asking us, remember what a p-value is it is how often you expect to see sample results like yours or ones that are more extreme if the null is true. So since our sample proportion was equal to, right, 5 out of 25, which is 0.2. So how often did a result like that or one even more extreme, meaning further from the null value, happen? Well, these two dots right here, right? These two dots represent the 2 times that the simulation gave us results like the one that we actually saw. So when we talk about a p-value is just going to be, in the last example it was 0 because we never saw results like ours. In this example, it's 2 out of 100, meaning the 2 times we saw results like that out of the 100 total times we tried it. So that is 0.02, right, or 2%. So what this literally means is if the null hypothesis were true, we would expect results like our sample or more extreme results about 2% of the time. Okay. So another way of putting this is if the null hypothesis were a true statement, then what I witnessed is something that happens 2 out of every 100 times. Okay? So that means that it's certainly possible that we happen to get this low sampling of positions at this company that just happen to have a really low number of women. That could have just happened due to random chance, is what this is saying. But it's also saying that it's not very likely, right? That there's about a 2% chance that that happened. So, again, let's remember how we ultimately make our decisions, right? We said we're going to use a 5% level of significance, right? So that means that our level of significance alpha is 0.05. And when we make this decision to reject or fail to reject the null hypothesis, we're basing it solely on, is the p-value below this level of significance or above? So we are going to reject the null hypothesis. And why are we doing that? Because 0.02, which is our p-value, is less than 0.05, which is our level of significance. So think of a level of significance as being kind of the chances we're willing to live with of rejecting a true null hypothesis. So because we calculated that we would only expect to see samples like ours 2% of the time if the null were true, since that's less than the chances I'm willing to live with of rejecting a true null hypothesis, that's why I make my decision to go ahead and reject. So again, to use the analogy that a null hypothesis is kind of like the defendant is innocent in a court case, right? You decide to reject the idea of the defendant's innocence if you're presented with compelling evidence beyond a reasonable doubt. Okay, so what is this reasonable doubt? Well, the reasonable doubt is kind of like the line for what constitutes reasonable doubt is like this level of significance, right? You have to decide as a juror, okay, what level of uncertainty constitutes reasonable doubt. And so that's kind of what this level of significance is like. Since we're under it, we reject. And then remember that when we write out a clear conclusion about our alternative hypothesis, we always say either there is or isn't enough evidence for the alternative. Well, when you reject the null, that means there is sufficient evidence at the 5% level of significance to suggest and then we can just go back to what we said in our alternative hypothesis, right? That the proportion of management level positions awarded to women is less than 40%. So to take it back to the context of this problem, right, we're essentially saying that it's possible that this company just happened to have a really low sampling of these positions and just a really low number of women in that one little sampling. That's possible that it happened randomly, but it's not very likely. I think there's about a 2% chance that that happened. And so what's more reasonable for us to conclude is that maybe there is something going on here, right? And we're not necessarily able to determine the cause, right? We don't necessarily know, like, is there real explicit discrimination? Is it more implicit bias? We really don't have the ability at all with this information to diagnose what's going on here. But what we've shown is that there is statistically significant evidence that the proportion of the time these positions are awarded to women is too low. All right, and so that's kind of where that, maybe that investigation can begin of why that's happening. All right, one last thing I want to touch on here with the same example is it says, and this is completely separate from all the other parts we just did, okay? So we really did finish the problem, but I want to ask one more follow-up, and that is, suppose the sample statistic was 7 out of 25 instead. Would the conclusion have changed? Okay, that's the question. Would the conclusion have changed? And so what I want us to understand here, if I go back to this, and let's use a completely different color so we know that we're talking about something totally different here. Use purple. Okay, So 7 out of 25 is 0.28, okay, 0.28. So what if the sample statistic was 28% instead of 20%? Would that have changed what we concluded? So going back here, like we said, here's 0.24, so right here is 0.28. If that were the case, then what I would have done is I would have counted everything from 0.28 and below. And as I tally that up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So what we can see is that 13 times out of 100, we would have gotten results like ours. And so what that would have meant is that the p-value would have been 13 out of 100, or 0.13. So in that case, we would observe that 0.13 is greater than 0.05, right? Comparing our p-value to our level of significance, alpha. So in that case, we would fail to reject the null hypothesis. Now, this language of fail to reject might seem a little clunky. You might say, well, why don't we just say we accept the null hypothesis? Understand that a hypothesis test will never have the ability to allow us to accept the null hypothesis. So either there's compelling evidence to reject it, or there's not enough compelling evidence to reject it. But saying fail to reject is different than saying accept, right? Failing to reject just means we didn't reach the evidence threshold. And to help you understand why this distinction is important, again, if you're on a jury, to use that analogy again, and you decide to acquit the person, you don't have to conclude that they're innocent in order to acquit them, right? In fact, our system is set up so that even if you suspect that they are guilty, but you judge that the evidence is not compelling enough beyond a reasonable doubt to say they're guilty, then you don't say that they're innocent, you just say that there's not enough evidence to find them guilty, right? So just like a juror can't necessarily conclude at the end that they know the person's innocent, rather they're saying there's not enough evidence to say they're guilty. So that's why we're either going to say reject the null, or we're going to say we fail to reject the null hypothesis.